Okay, let's continue to the next part using Z transform. Well, let me recall this a little bit. So the process of finding Z transform of a system that you use the method of zero order whole for the control input. First, you need to find Z transform of this part, okay, of this part, and then you can just directly multiply it by this term. Okay, it's very easy. Let's see one example here of discrete transfer function of first order system, and the question is what is the discrete transfer function of this G of S preceded by a zero order whole. Okay. So for solution here, first you find the G of S over S, and you convert it into canonical form. Okay. I hope you still remember how to do this, and then find the inverse Laplace transform of G of S over S. So in this way, let's say if we don't use tables, if we want to find Z transform step by step, we don't need to use table, then you can follow this process. So in here, we can find the inverse Laplace of this transfer function, this whole transfer function. Then we get the answer in the time domain. Okay, 1 over S we transform to be 1 of t, a step function. 1 over S plus A transform to be e to the minus at time a step function. Okay, in the time domain. Then we sample this function. Okay. Okay. See, you can see when we sample the function in the time domain, the value is still the same as the continuous one when we evaluate at the sample time kt. And then we can apply Z transform for this function and this function. So Z transform of step function, you get 1 over 1 minus Z power minus 1, but you can rewrite in this form, right? And Z transform of this exponential term becomes like this. Okay? And after then, you can compute GZ of the whole system by multiplying the result that you just found here by this term. Okay, this term is just the same as 1 minus Z power minus 1, right? Yeah. And then after you make the simplification, you can have G of Z as this. Okay, so this is the transfer function or the Z transform of the system that you have zero order whole in the control input. Okay, so the input is stair-like control input, right? Stair-like curve, not a smooth curve. Let's try with simulation. So let's simulate the discrete system using ITC-DCLab, as you can see here. So in ITC-DCLab it's a little bit difficult, okay? More difficult than MATLAB. You can directly well, you can directly find the transform from here, and then you can simulate easily. But for Scilab, you cannot have the function that convert from continuous transfer function to discrete transfer function. You need to find it manually first, and then simulate it to see the result in the time domain. So let's try with Scilab to see. Oops, did I? Okay, so first let me explain line by line of the code here. First, define U as input by this function. Actually, this is just step function, and you have the step function, but for in a discrete time, you have 200 samples, so 1, 2, 3 up to 200 here. Okay, so just step like this. Yes, like this. Okay. Oh, one here as well. Yes. So it's like step like this. Okay. I use a different color. And here Z is defined as variable for polynomial. Okay, like this. Z is going to be used here, but then let me explain capital T. Capital T is sample time in between here, so capital T is 0.04 second, and T, if you want to find the actual time, okay, T equal to capital T times the index from 1 up to the length of U. So the length of U is 200 actually. So this one is the same as 200. Okay, or maybe red is better. Yep. So here is just same as 200. A is equal to, the A is from here, A for this A, and GZ, well, GZ is here, 1 minus exponential of minus AT over Z minus E exponential of minus AT. So GZ is defined that way, and then you transform the G of Z, the polynomial, into state space. This one is state space. Okay, transfer function to state space. Once you have state space object, I call it object to represent it in the code. Okay, or model. Once you have state space model, then you can compute it using discrete simulation. Okay, discrete simulation of the state space with the control input U here. Okay, and finally you have the output as H of H3, while actually usually I denote output as Y. Maybe it's better I will change it to Y. Output, and then you can plot the graph with x-axis as time t, and yeah, x-axis as time t, and then the y-axis you have u and x. U is input, x3 is output. Okay, so you plot these two graphs together on the time domain. So now you can try. Okay, so next let's try exercise number 2. Okay, example number 2. This is the second order system. Again, the question is to ask you to find the discrete transfer function of g of s equal to 1 over s squared preceded by 0 or the whole. Now you try on your own. Okay, so for the problem, similarly to the previous one, first you need to find g of z, which is equal to 1 minus z to the minus 1 times z transform of g of s over s. So g of s over s equals to 1 over s cubed, and z transform of this can be found in table. To be exact, actually you can find z transform of 2 over s to the 3. That's why you have 2 here. Yeah, actually this is found from table, and therefore the final g of z equal to this. Okay, I mean this time this, and then you can easily simulate it using ITC-DCLab, following the pattern or the step by step of the previous example. From here, the difference only on here on the function g of z here. So just change this to be this formulation, then you can easily simulate it. Alright, so that's all for today.